we need to find is the heat transferred during the compression. We have an isothermal compression, meaning that the temperature is constant. So if we apply the first law, we have the change in internal energy equal 0, and the heat equal the work. Why these things become 0? Because we can always calculate the change in internal energy using this expression. And since the delta T equals 0, everything equals 0. If you do not remember well, you can open the slide, okay, lecture slides, then you reread once again. Now the problem becomes, uh, can you turn off your mic? Bạn nào đang mở mic nhỉ? Can you turn off? Now the problem becomes finding the work done by a compression, isothermal compression. And for this we know, right? For this we know that we can use this formula to calculate the work done by an isothermal compression. Then we know the temperature, it should be in kelvins. Okay, we can calculate the work, the work, and then the heat transferred. And when we see that if there's a minus here, it means that the system loses energy as heat. Yeah, the system loses energy. Okay, so this is the question 4. Now I receive only the solution for question 4. I will wait a little bit more, and then I will correct the number 5 and 6 at a row. Here, Nguyễn Nhật Anh sent me the solution for question 6. So I suppose that no one can do the question 5. Okay. Here for the question 5. We have a problem of submarine rescue. So we need to rescue people inside a submarine at depth 80 meters. At depth 80 meters. Then the problem is that the temperature and the pressure at the sea level will be very different than what we have at depth 80 meters, right? And one consequence is that when we lower the chamber to rescue people, by inside of the chamber we need oxygen, right? We need air. And if we fill in the same amount of air that we have at the sea level, this amount of air will not be sufficient to occupy the same volume of the chamber at depth 80 meters. So you understand? Because if we apply the ideal gas law PV equal nRT, you will see that if we have a change in pressure, so an increase in pressure, a decrease in temperature with the same amount of mole of air, then the volume at sea level will be much bigger than the volume that the same amount of air occupies at depth 80 meters. This is the problem that we need to solve. Now, firstly, if we calculate the air volume at sea level, so before we lower the chamber, exactly the volume of the cylinder chamber, and then you should be able to calculate this one. So 12.6 cubic meters. Now we need to determine the pressure at depth 80 meters. Okay, at depth 80 meters. So we can use this formula. It is already given. This is actually the atmospheric pressure plus the pressure generated by the seawater at depth 80 meters. So you use this formula. Rho here is the density, G, gravitational force, so you know already. The depth is 80 meters. Okay. And you should be able to find this result. But please remember, like I said many times, when you write down a value, you should write also the unit associated with this value. Here, this is a typical exercise that shows you if you forget the units, you will make a big trouble. Here, I have the density measured in kilogram per cubic meters. I have the gravitational force measured in meter per second squared, and here I have meter. If I consider only the dimension, okay, here what I have is the atmosphere, and if we simplify this thing, what do we have? We have kilogram per meter per second squared, and this one is actually Pascal, okay. Then what we have here is atmosphere plus Pascal. If you forget, then you will have a wrong result, because here you calculate using atmosphere, but here you calculate using Pascal. So you have to do the conversion, right? By dividing what we found to this unit. Now what we have is that the Pascal can be written as Newton per meter squared or per joule, or also joule per cubic meters, or also kilogram per meter second squared. This is Pascal. This is Pascal. And 1 atmosphere can be convert, converted to Pascal also by multiplying to 10 power 5. Then you should be able to find the final result for this one. Now if you use the ideal gas law, we should be able to find the air volume at depth 80 meters. Okay. Now if you see, if we use the same amount of air that can occupy the whole chamber at sea level, then at depth 80 meters, it can only occupy 1.16 cubic meters. So we see a decrease in volume, right? And we can calculate this decrease in volume. And we know how much of more of air we need to release more to the chamber. So this is the final result. Is it okay for this? Do you have any questions? No? Then I wait for 5 more minutes. Meanwhile, I will check uh, the solutions that you sent me. Okay, I will correct the question. Here I received one more solution from Trịnh Ngọc Trường An. Good. Now the question 6. We have a closed cycle, if you remember, with the pressure and volume. This is a PV diagram, right? A closed cycle. And what we want to study is the characteristics of each process, AB, BC, CA. And here we use N moles of the gas sample. Firstly, we need to calculate the number of moles of the gas sample that we use. So if we read carefully, we see that we have enough information to calculate the number of moles of the gas sample at point A using the ideal gas law. Okay, so this is applied for the point A. Please remember that if we measure the pressure in Pascal, then the gas constant should take this value and this unit. If you solve it correctly, you should be able to find 1.5 mole. 1.5 moles. And since we use the same number of moles, we use the same sample for the whole process, for the whole cycle. So the number of mole at point A should be equal number of mole at point C and also number of mole at point B. Then we can establish a relationship between the point A and point B to be able to find the temperature at point B based on information at point A, like this one. And then point C also, you should be able to find it, the temperature at point C, using exactly the same way. Good. Now, for the question D, we need to find the net energy added to the gas as heat. Okay. If we still remember for a closed cycle, what do we have? We have a change in internal energy equal 0, right? Change in internal energy equal 0. And this one, we will have the net heat equal net work done by the gas. Good. And finally, we will have this result, because the net work done by the gas is actually the area of this triangle, and you should be calculated easily. Okay, if you already finished number 6, then I give you 10 more minutes for question 8, question 10. Yeah. If you want, you can take a break, and then after 15 minutes, we will correct both question 8 and question 10. Okay, please come back. Here I receive a solution for question 10 from Vương Đăng Thái, right? Good. This is question 10. Question 8, I also received 2 answers. Yeah, let me check it. Very nice. Good. Nguyễn Quang Vinh did it very well. Trịnh Ngọc Trường An. Yeah, Trịnh Ngọc Trường An also very good. Nice. So please come back. I will check if you are still here. Nguyễn Xuân Tùng.
Dạ.
Okay, have you done the question 8 and 10?
Chưa.
Có làm không mà chưa?
Có, nhưng mà em không biết cách làm.
Bài 8 nói gì nào? Tóm tắt đề bài tôi xem nào. Bây giờ mới đọc đề thì còn làm cái gì? Tất cả những trường hợp này mà trượt không bao giờ tôi cứu. Phải làm thì mới ấy chứ. Đâu có làm đâu mà kêu em không biết làm. Đọc đề còn chưa đọc. Okay, I will correct the question 8. So this is the question 8. What we have in question 8 is that we have 2 containers connected together by a valve. At the beginning, the valve is closed. What we know is that the container A is 4 times smaller than the container B. And the container A has a temperature. The container B has a different temperature. What we know also is the pressure before opening the valve of the container A and B. And what we know also is the total number of moles of the gas remains constant even before and after the valve is opened. Right? The total number of moles of the gas in both containers is constant. So this is what we know. When we open the valve, then we keep the temperature remain the same. The temperature of container A is the same, the temperature of container B is the same. What is changed is the pressure, right? Now we have only one final pressure. And we need to find this pressure. If we start writing the number of moles of the gas in container A using the ideal gas law. So this is the expression for NA. And this is the expression for NB. Okay? Because we know the volume of B is 4 times bigger than A, then we can replace for VA here. And if we calculate the total number of moles in both containers, we will have this expression. Please follow the mouse. Then after the valve is open, we will have a different pressure and different number of moles, right? In both container A and container B. The others, so all the parameters remain constant, remain unchanged, I mean, right? We continue. We can establish an expression, for the total number of moles in the gas after the valve is open. So this is this one. So we expressed maybe NA prime or NB prime. It's up to you. Here I choose to express NA prime. Okay, NB prime as a function of NA prime. The purpose is that now we have only one unknown, which is NA prime or NB prime. It's up to you, okay? And since there's only one unknown, others we already know the values, we equalize this equation. Then we will be able to establish the final expression for NA. Here, it seems a little bit complicated, but if you see, V, we know it. R, we know it. Right? PA, here actually VA, okay? VA, we know it. PA, we know. TA, we know. TB, we know. TB, we know. Well, everything we know. Then, theoretically, you should be able to find the NA prime. Once you have the expression for NA prime, you use once again the ideal gas law to be able to find the pressure. And the final pressure is this one. Here, what I recommend you is that you develop the formula, all the formulas until the end. When you have the final expression like this, then here you start to replace all the values. If you do like this, for sure you will get at least 90% of the points. And here, if you do it wrongly, for example, if you have a problem with the calculator and so on, then you will lose only 10% of the point. But if you replace the values from the very beginning, and if you replace it wrongly, everything after that will be considered as wrong and you got 0. So you see, cái phương pháp mà tôi khuyến khích các bạn đó là phát triển tất cả các cái biểu thức cho tới khi mà ta có một cái biểu thức cuối cùng đó, rồi sau đó ta mới thay số vào, thì lúc đó các bạn chỉ phải tính toán một lần. Và nếu như mà các bạn biểu thức cuối cùng mà đúng và các bạn thay số sai ấy, thì các bạn cũng đã được 90% số điểm rồi, bởi vì chúng tôi biết lúc đó là các bạn hiểu bài. Còn nếu như mà các bạn thay ngay từ đầu này mà các bạn sai một cái gì đó thì tất cả các phía đằng sau là coi như là sai hết. This is okay. This is for the question 8. Now we continue question 10 and question 12. Question 10 and question 12. Let me check one thing. Okay, I think I can correct the question 10 right now. Let me check if someone sent it to me. Yeah, question 10, I have Bảo Quốc and Phương Đăng Thái. 62. Okay. Thái ơi. Thái ơi. Thái ơi.
Dạ.
Vương Đăng Thái ơi, em làm bài 10 của lần trước à?
Dạ, đâu
Em làm bài 10 của chương 1 à?
em vẫn làm của cái file.
Sao lại file ý? Bài 10 chương 2 cơ mà.
Em là người.
Cô cho xem lại đi nhá. Thế, tuần trước không học hay sao mà bây giờ còn đi làm bài 10 của chương 1? Trời ơi thanh niên. Recheck ok Thái.
Vâng.
Sợ các cậu thật đấy. Đang học chương 2 giờ lại đi gửi tôi bài chương 1. Good. Then okay, I have only one solution. Here we go into a problem of identifying the gas. If we know the density of the gas at a certain temperature and pressure. Ok. Bài 10 này các bạn phải download file mới này, file cũ của lần trước là nó bị nhầm đó. Now, what we know is that the pressure, the temperature, and the density of the gas. Actually, the density of the gas, the rho here, is the sample mass divided by the volume. Then we have the density. Okay, the sample mass divided by the volume. Then we have the volume. That's all. This is what we know. Now we can use the ideal gas law, but we have to rewrite the ideal gas law based on what we already know. What we know is the density and also the number of moles that can be written like this. Okay, then if you write it here, you will be able to find an expression, a new expression for the density. Okay, PV equal nRT, then you replace firstly the n, you write it like this. So the rho here is actually Yeah, you should be able to find. Is it okay? When you find it here, you can find the root mean square speed. If you do not remember what the root mean square speed is, so I invite you to reread my slides. Okay, please reread my slides so then you know what the root mean square speed is. Good. Root mean square speed can be calculated using this formula. Okay, so the root square of the 3RT over m. Then you see here we have RT over m. Here we have m over RT. Then you can express the root mean square speed in terms of our pressure and density. In terms of pressure and density. Now, if we convert the density and the pressure into the SI unit, this is what we have. This is what we have. Is it okay? We should be able to calculate this one. Here, once again, I remind you that the Pascal can be expressed also as kilogram per meter second squared. And here we have kilogram per second squared, then kilograms over kilograms will be cancelled out, and what we have is meter squared divided by second squared. Then we have meter per second at the end. And what we need to find is the molar mass, because we want to identify the gas, right? Then the molar mass you can calculate it because we have this already, but we know now we know everything, right? We know the rule, we know the gas constant, we know temperature, we know the pressure. We just need to calculate it correctly. We should be able to find that the number of molar mass, the value of molar mass of our gas is 27.9 gram per mole. And we know that this is nitrogen. This is nitrogen. This is for question 10. I give you 5 more minutes to do the question 11 and question 12. Okay, we will do also the question 11. 5 minutes and then I will correct it. Okay. Uh, 11. Nguyễn Quỳnh Trang and Đào Minh Anh. Root mean square. Đào Minh Anh gửi bài mười mấy đây? Bài 16 à? Ok, bài 16 thì ta tạm thời đây nhé. Bởi vì 16 thì thực ra trong lý thuyết thì tôi chưa nói tới các cái ngoại trừ root mean square speed thì tôi chưa nói
Thầy
tới
ơi, bài đấy
các
là
cái
bài
khác.
10 ạ.
Quỳnh Trang á.
Không ạ, Minh Anh ạ, của Minh Anh ạ. Đấy là bài 10 ạ.
Rồi tôi biết rồi. Tôi đang nói cái bài của Quỳnh Trang. Bài 10 tôi xem rồi. Good. 12 của Nguyễn Quang Vinh. Good. Okay, now we correct both question 11 and question 12. Question 11 and 12. Now for 11, but we need to find the translational kinetic energy. Okay. And we know that it depends only on the temperature. Only on the temperature. It means that if we know the temperature of the gas, we should be able to know also the translational kinetic energy. Okay. I have a question or something. Now, for the average translational kinetic energy per mole, per molecule, per molecule, we can simply apply the formula given in the lecture slide. This one. We have here is the Boltzmann constant, and here's the temperature. Okay, this is the Boltzmann constant. Good. And this is at 0 degrees Celsius. Here, this is at 100 degrees Celsius. You have to convert it into Kelvins, of course. Okay. Now, if we want to have the kinetic, translational kinetic energy of 1 mole, so I write it here, K mole, you should, of course, multiply the average translational kinetic energy of 1 molecule per the number of molecule in 1 mole. So actually this one and this one at 0 degrees Celsius, you should be able to have the final result. We do the same. I do not write it down here. We do the same for 100 degrees Celsius. Exactly the same. 3 here, good. 7.72 here. And the final result, I don't know how much. You calculate it by yourself. Okay. I think in the... Now we go to the question 12. So for the question 12, what we know is that the average energy of the escaping molecules, so epsilon, that will be equal to the ratio between the heat of vaporization and the number of molecules per gram. Please do not be confused with the number of mole, okay? The N is the number of molecules per gram. Number of molecules per gram. And if we calculate for water, what do we know? We know that the molar mass of water is 18 gram per mole. Okay? The molar mass of water is 18 grams per mole. And we also know that, of course, in 1 mole, we have this number of molecules. So then, in 1 gram, we can have this number of molecules. But we just divide the number of molecules per the molar mass, right? Then this is the number of molecules that can be found in 1 gram of water. Good? 1 gram of water. If we have this, we should be able to calculate the epsilon. So the escaping energy of molecules. Is it okay? The heat of vaporization of water, you can find it online. Yeah. Or in the previous part, you can also find it. So this is the epsilon. Now what we need to know is the ratio between this epsilon and the translational kinetic energy. Then firstly we need to calculate the translational kinetic energy, the average one I mean. And we apply what we saw previously, this one, and you do the calculation correctly. You replace the Boltzmann constant here. Please do not forget the unit, and here the temperature should be measured in kelvins. Is it okay? Then you should be able to find the ratio. Is it okay? I will check if you do it correctly. I think okay. And do you have any questions? If there's no questions, then I suppose that you understand already. For exercises that we do not have time to correct together, I encourage you, I recommend you to solve it by yourself. Okay, to solve it by yourself. Of course, at the end, after all lectures, I will upload the solution for all exercises. But it will be not helpful for you if you do not do it by yourself. So, is it okay? Is it clear? If there's no questions, then I thank you for staying with me. And see you in the next lecture. Okay, you can stop here, and then I will continue with another group.
Bye, teacher.
Bye bye.